Hello, we're going to investigate a source of inharmonicity in the piano by simulating two strings, one flexible and one stiff. And these strings are designed to mimic the behavior of a C4 key on a piano. And here's the dimensions and the parameters. This problem has been solved in a variety of places by a variety of methods. Philip Morris provides an analytical solution in his book, Vibration and Sound, for the flexible string, which I've used. Nicholas Giordano provides an explicit numerical method for solving the problem. Again, I've used that one elsewhere. However, in this video, I'm going to use a method by James McDonald from the University of Delaware. Now remember, these simulations, however artificial they may seem, are designed to gain insight. The flexible string is described by this differential equation, which is the wave equation, second order. Two boundary conditions. The string is held constant at the left end and the right end, where the bridge is. It has two initial conditions. The string is initially at rest, and initially the speed of the string is prescribed, the speed being a consequence of the hammer strike. The stiff string is described by a fourth order differential equation, which is the same as this one, except for this extra term. It has two extra boundary conditions. The second partial derivative at each end is held at 0, which is indicative of a hinged connection. Alright, take a look at the initial speed. This is the consequence of being struck at 1/8 of the length of the string, which is right here. It generates this sort of a initial speed. Now keep in mind that this shape is artificial. It's chosen such because it gives results that match other simulation results and also other physical results. The magnitude of the speed, again, is scalable, so it doesn't really make any difference. It's artificial. And again, remember that the object of this simulation is to gain insight. Here's the initial speed and its representation in the frequency domain. This is necessary for the solution by Professor McDonald because he needs to approximate the initial speed over here by a Fourier series. And I show here the initial speed in green, and then the little circles are what the approximation looks like. I show this representation in the frequency domain because in theory, and actually in practice too, you could just pick one of these harmonics, feed it to the simulation machinery, and get a response out. You could do it for all these different harmonics separately, and then add up the results, so you get the same thing as if you would do them all together. Now, here's a picture of what we're going to be doing. We're going to feed this initial condition of the speed and the initial position to the string dynamics model machinery. It's also represented in the frequency domain by this Fourier series. The output is going to be the wave shape as a function of time along that axis and position along the string along that axis. But it also can be represented by a force in the time domain, and then we could take the line spectrum of that force. So this particular information can go into this information in the frequency domain. And we'll compare the spectrum of the stiff and the flexible string and take a look at the consequence of inharmonicity. As I mentioned before, we could have picked just one of the harmonics and fed it to the string dynamics model machinery. This For example, this is the 15th harmonic, just for example. It corresponds to initial speed down here, which is completely unrealistic. The resulting wave shape in the time and the position domain, again, is pretty unrealistic. The frequency domain representation of the force, however, shows that this particular harmonic shows up with a spike for the flexible string at the 15th harmonic, but the 15th partial for the stiff string is displaced because of inharmonicity. Okay, let's start the simulation. We're going to strike the string. There, we did it. Generates this pulse, which starts to move along the string. There's a little separation here between the green and the blue. The green is the stiff, the blue is the flexible. Here's a reflection. Notice there's a little bit more separation after that reflection. You have a little bit of underdamped behavior right there too. Another reflection. Now we're getting more underdamped behavior. We've got a peak and a valley here. Also more of a lead in the stiff string. Another reflection. More underdamped behavior and more of a lead. This is the last reflection we're going to look at. Okay, this is the final moment of the two periods that we just looked at. Notice that the flexible string comes back to its initial rest position, whereas the flexible string is showing quite a bit of lead and quite a bit of underdamped behavior. Here's the summary of what I've just said before, and I just want to note that these results, this kind of behavior is similar to that seen in the simulations of Morse and Giordano. Now you can go through and calculate the lead of the stiff string over the flexible string as a function of time, which I've done over here in this graph. I'm plotting the lead of the stiff string versus the time. This vertical red line here represents a reflection. Here's the reflection after one period, reflection after two periods, so forth. The thing to pick out of this graph is that at each reflection, the level of the lead takes a step change, increase. So what's happening is the effect of the reflections are causing this lead. So the stiff string is propagating more quickly as time goes on. The force on the bridge is proportional to the slope of the string. If the string is flat, as it is initially, there is no force. If the string has a slope that's negative, then we're pulling up on the string. If the slope is positive, then we're pulling down. You can see initially over here, both the flexible and the stiff string have basically zero force on the bridge because they're both flat. But then at the reflection, you get this whiplash effect and you get these peaks in the force. Then as the peak propagates the other direction, the string slope at the bridge is relatively flat, so you get a low force reading. In fact, the flexible string by blue here shows a lot less than the stiff string because there's very little underdamped behavior on the flexible string. The other thing you can see from this graph is that the peak of the flexible string is higher than that of the stiff string. In other words, there's a higher force exhibiting at the reflections. And this is because the flexible string, because of its flexibility, is making much sharper turns when it's reflected and inverted. The stiff string, because it's elastic, resists changes like that, and therefore the peak is not as strong or as high. This idea of elasticity is the tendency of the string to maintain its shape after or return its shape to initial conditions after a deflection. The force for the stiff string leads that of the flexible string. And this is supported by the plot in the time and the position domain. For example, here we have the amplitude of the string plotted versus time and versus position along the string. Start out, you can see this line along the back here, the flat line. That's the initial rest position. The string is struck, and then this peak is developed, this pulse, which moves towards the bridge. While it's moving towards the bridge, the slope at the bridge over here is basically zero, which is what we see here. When the pulse reaches the bridge, now you see we're pulling up on the bridge. The slope is negative, and this spike is generated. Then the string is reflected, and now suddenly we're pulling down on the bridge, which is reflected by this negative peak. Then as the pulse propagates back to the other end of the string, you can see that the slope is relatively flat here, which is represented by this low level of force at this point in time. Finally, let's take a look at the line spectrum of the force. The first peak here is located at the fundamental, which is at 261.6 Hertz. The two peaks pretty much are the same, at least given the resolution of the computation in this simulation. As the peaks get higher in frequency, you can see there's a separation here. For example, I think it's the 6th partial and the 6th harmonic. The red line is the harmonic, and the flexible string's peak is right on the harmonic. However, the stiff string's partial is displaced to the right. It's a higher frequency. This displacement gets bigger as the frequency gets bigger. Note, for example, we have nothing here at the 8th harmonic because we are striking the string at 1/8 of its length. We also have diminished force, partials, and harmonics out here around the 16th harmonic. For example, now we see that at the 13th harmonic we have a displacement almost equal to the fundamental, which is the separation between these two red lines. Over here we have the 17th harmonic by this blue line, and then here is the peak for the 17th partial. So now the dispersion or the displacement is actually greater than an amount equal to the fundamental frequency. So we're seeing inharmonicity in this spectrum, and we're proposing that it is coming from the reflection at each end of the string because of the elasticity. Okay, we can listen to those collected values. I collected the waves, and I can send them through the MATLAB sound feature, and we'll see how they sound. That's the flexible string. That's the stiff string. And then here is the C4 on a Yamaha P120. That completes the simulation and it completes the presentation. Thanks for watching and listening.